All right, we're going to have a conversation here about a game that Steve wrote that basically sparked computer games and everything that we're doing today. So what we're gonna this is a big history lesson, this whole thing here. So so make sure you guys get your passport stamped. I don't know if that actually is a game here, like stamping the passport. All right, good. Because I was hoping it looked really fun. So okay, so we'll start. This is Spacewar was started in 1961, and so we'll go back a little bit before Spacewar to like what happened before Spacewar. What were you like? How did you get an interest in computers, and what kind of led up to the creation of that game?
Well, I went to Dartmouth College for 4 years, and like many people, I didn't graduate. But I got an excellent education, and one of my professors was John McCarthy. I was majoring in math, and he got me a summer job between my junior and senior year at MIT, where I did various things. I wrote some Fortran programs. Fortran had just come out. It had no numbers. It was just Fortran.
Nice. It wasn't 77, the one that like anyone would remember.
57.
Okay.
So I did that, and I thought computers were fun, and John seemed to think that I had some aptitude in the thing. So I went back and did my senior year and didn't quite finish up. But he had offered me a job, and he didn't care. And so I started working at MIT for John McCarthy. He and Marvin Minsky had just started the artificial intelligence project. And so we hand-compiled a language that talked about symbolic expressions for a couple of months. And John then wrote a function that he called the universal M expression, which described an interpreter which would interpret the language. And the language got named Lisp for Lisp processing language. And so I looked at what John had written out, and since I'd been hand compiling that sort of thing for a couple of months, I said, oh, I can do that. And John didn't object too much, although later on he said, that was a little premature. But
That's funny. So that was Lisp, and I guess that started in '58 and went.
The first version was running in December of '58.
Okay.
And there was a rather disastrous. Well, there was an exciting seminar. Jim Slagle, who was a blind graduate student and very smart, needless to say, was working on doing symbolic integration in Lisp. And so he had a seminar which explained what his functions looked like and how they were going to work. And those of us who knew the interpreter were sitting in the back, and we started muttering, oh, that's not going to work. The interpreter won't handle that. And so after considerable agony, we had figured out a way around it that didn't hurt too much, but was hard to compile.
He was stressing the language, and you guys had to find a way to make
Yeah,
it work.
well, I mean, he had just used it in a straightforward way, and since all of us had some math background, we thought that if it was straightforward and obvious, that's the way it ought to work.
You should be able to do that.
So anyway, the fix that we invented was called the function funarg hack, because it was felt to be despicable because it was rather complicated and it wasn't clear how to compile it efficiently. But it made the interpreter work and it made his function work. So I rewrote the interpreter in the spring of '62 or '52. Okay. No, it'd be '59. To work right, and he got his function working and he got his thesis.
Great.
So at the time, the big computer of the time that we were using, the biggest computer available, was an IBM 704. Now this is a vacuum tube computer that needed about 2,000 square feet of false floor and a very enthusiastic air conditioning system to work. And it was, it didn't cost MIT the full list price, but the list price was about $2.5 million.
Wow, that was a lot back then.
And it translated to about $200 an hour when I was getting paid $10 an hour.
Wow,
So-
don't mess around.
The computer was much more expensive than me.
Okay.
So I had to wait for the computer a lot. We'd prepare card decks. Lisp was written in assembler. And so we'd prepare card decks, and it ended up being about 4 big trays of cards, about 12,000 cards. And we'd then take them down to the operations staff and present them with a card explaining where it was supposed to stop to the operations staff. And they would take the trays of cards, put them on tape, hopefully not dropping them, although occasionally they did, and feed it to the computer, which would typically assemble a symbolic deck, and then run it. And when if it didn't run the way you said it was, if it didn't stop at the place you said it was going to stop, they would give you a dump of all of memory, which was something over 200 pages of octal numbers.
Octal. Base 8.
This is hex. This is what.
Yeah. Pre-hexadecimal.
And so then you would take the assembly listing and the octal dump, and you try and decode what was going on. And one of the things that I learned there, which I think fortunately none of you have had to learn, is all about arithmetic. Because the 704, for reasonable architectural reasons, had 1's complement arithmetic, 2's complement arithmetic, sign magnitude arithmetic, and excess 200 octal arithmetic.
You have no idea how tedious it was to program on these computers back then. I think most of your time was not spent programming, but was just dealing with getting things in and out of the machine.
There were complications, but anyway, it took a couple of hours to analyze the dump, since it was list structure and you had to chase it all down. And then you could change the program and try again. So typically you got maybe 1 run a day, maybe if you were exceedingly lucky, 2 runs a day.
That's
But
slow.
it usually took more than 1 run to kill an interesting bug.
Wow.
There was an additional thing. You couldn't assemble things. It turned out, with the vacuum tubes and the mag tape at the time, getting 12,000 cards onto tape correctly was not a sure thing. So the usual practice was you'd get the cards on tape, you'd get an assembly, you'd find a bunch of assembly errors, you'd discover some of them were due to not reading the cards correctly. So you'd make up a bunch of octal correction cards.
Oh, geez. Overwrite, patching your code.
Yeah, so you would patch the code. And then as you found bugs, if they were easy to fix by patching, you would make an octal patch. And if they required something worse, then you'd go through the business of edit the card deck, send it through to an assembly, fix the assembly errors, and then get back to debugging.
Wow. So somehow you got to make a game, though, while you're going through this crazy, tedious process.
Well, so anyway, that was where I started.
With the tedium.
And then in 1961, something happened.
Yep. In January, right?
No, it was, yes. In January, the Russians put a man into orbit.
Yep.
In April, the U.S. managed to get a man into orbit. The space race was on and very hot.
Yeah.
Then in the fall of 1961, Digital Equipment, who had been had a revolutionary transistorized computer that was only the size of 3 or 4 refrigerators,
Much smaller. Yeah. Didn't take up a room, so that's good.
It didn't fit in your pocket either.
Yeah.
Anyway, they donated one to MIT. And it was down the hall from where I was working. And so I looked in on it. And a bunch of people, there were some undergraduate research assistants who worked on it. And we were all members of the Model Railroad Club. So I looked in on it and saw what was going on. Now, one of the first things that was going on was Marvin Minsky wrote a program that he called he called Tripos. And it put 3 spots on the screen, and the spots were influenced by the setting you put in the data switches when you started the program. It was kind of a kaleidoscope, and what you learned was that a lot of the patterns were uninteresting. Some of the ones that were interesting for a while, but they all evolved, and they got more and more and more random as time went on. It was fun to play with for a couple hours, but it got boring after a while. And I started talking up the idea that what we really needed was a better demonstration program.
A demonstration. Just make a demo.
Yeah.
You need a really cool demo for this machine.
Right.
Okay.
Now, while I was talking, the Model Railroad Club guys had cornered their boss, Professor Jack Dennis, and insisted on translating the assembler that they had on TX0, which was next door, for the PDP-1. And they did it over a weekend.
It's pretty fast.
Yeah, well, they knew the design that they were copying, and they agreed and managed to adhere to, we're not going to change a thing in the design.
Right.
So it was just taking code they'd written once, writing it again for a different processor.
And then getting it in, though, was on switchboard? They
No,
didn't have to do DECs, or?
The way you assembled things there was an assembler on the PDP-1, but it was kind of lame.
Okay.
It had originally been designed to work in 1K of memory, because that's what was on the prototype.
Right.
That's 1K words, big 18-bit words. So they had the assembler, and then they added some other things. They took their debugger, translated that, and then they had a utility program that would take that you ran after the assembler that would punch out your symbols, the assembler symbol table, onto the tape. And they had this debugging program that would read in your program and read in the symbol table. And it would do online assembly and disassembly in terms of the symbols you would use for writing the program, not glorious octal.
Oh, great.
And this looked like an interesting way to use a computer. It looked like it was going to be a lot more fun than reading dumps.
Yeah.
So I really wanted to try it. And we talked up what was a better demonstration program, and I started promoting the idea that something that taught people how to fly a spaceship would be a good thing.
Because of what was happening during that year.
Well, and also it would sort of fit.
Right. And you wanted someone else to do this.
Well, I was hoping someone else would do this. But in the style of such things, the usual reaction was sort of like, yeah, that's a really good idea. Somebody ought to do that. Somebody who really understands the idea. Why don't you do it? So I was shamed into writing some code.
Yeah. You had to. You didn't want to start it until you got some math code, though, right?
Well, I was sort of cornered into writing it, and so I had to think about how it was going to work. And I discovered, after a little poking around, that I could use one vector for the direction that each object was pointed,
right,
and do the sine and cosine of that vector once per cycle, and then do everything else in terms of the components of that vector.
Cool.
And So what I got working at the end of 1961 was a program that displayed two spaceships on the screen, and seemed like it needed some torpedoes, so it had torpedoes that would blow up spaceships and other torpedoes, and would sail around the screen. I put this up, and people tried it, and told me I should change this and change that. And so I changed some things and fixed things up. And then Pete Sampson looked at my stars, which were very random, and he thought that they were horribly unrealistic. And so he coded up a star chart and presented me with a program that he called Expensive Planetarium. So this was a clever piece of code that took 2 pages of an assembler and a big table. But so I put that in, and we had real stars. And Dan Edwards, who had worked with me on the LISP project and who was deeply involved in the first garbage collector, looked at my display code, which was interpreting cryptic 3-bit codes for the outline, and he figured out a way to speed it up. He wrote what is apparently the first runtime compiler, which took the cryptic definition and compiled exactly the right code to keep the display on the computer running at full speed.
Which was, what, 60 frames or 50?
Well,
there was a decay on the points, right?
It was the world's simplest display interface.
Yeah.
You put X in the accumulator, Y in the I/O register, give the display instruction, you get a spot on the screen, and 50 microseconds later you can do it again.
So it's 50. Basically,
50
the
microseconds,
refresh, yeah.
But you just got a spot on the screen, and it decayed. And so if you wanted a fixed object, you had to keep redisplaying it.
And those ships were made up of a bunch of little dots.
Yes.
And you had to do instructions per dot to make the whole display look like it was.
But he compiled his code that did an add, 2 shifts, and an add to go from the spot you were on to the next spot.
Like a simple Bresenham almost.
Yeah.
Like, okay.
So he added that, and that gave us enough time to calculate the effect of gravity on the spaceships. But we didn't have enough time to calculate the effect of gravity on the torpedoes, so we decided they were photon torpedoes, not affected by gravity.
Yeah, just go right through everything.
And so we bundled all that together and did some more debugging, and in order to deal with the people who said, you should change this parameter, change that parameter, you really ought to change things, I put all the parameters that affected the pace and the size of things, the number of torpedoes, in the first page, which so as that people could change it from the switches to suit themselves. And nobody did.
Yeah, we want to be able to change this and that and the other, and you're like, here it is. And they're like, okay, well, whatever. We don't want to flip switches. I mean, it was complex to do this stuff back then, so.
Well,
you know,
most of the audience understood translating
university
from
programmers.
octave to switches.
Here's the
yes.
switches. That's how you programmed
the console. The test word is where you control the Minskytron. On Spacewar, the left 4 switches and right 4 switches were the controls. However, if you sat at the console, you had to turn your head to look at the display, and you got a crick in your neck if you played for an hour or 2. So one of the first things that everybody did was add a separate set of boxes that allowed you to control Spacewar. They're handheld ones.
He's right there in the middle, by the way, you can't
that's
see him.
the back of my head. That's Alan Kotok, who didn't write any of the code, but was one of the ones who provoked
One of the
it.
Spacewar 6, right?
He actually, well, he sort of triggered my getting
He went and got the math code, right?
He took away my last excuse for not writing the code. I said I didn't know how to write sine and cosine routines. So he got a hold of sine and cosine routines and said, now what's your excuse?
Yeah, do it now. Write the demo. By the way, you saw that wasn't a keyboard that he was putting the game in.
And that's Shag Gretz, who worked on, who tinkered the explosions to look right and gave a paper at the users group meeting in May of '62, and we put Spacewar in the users group library.
His name was Shag, and yours was Slug, right?
Yes. He was apparently not very happy about his first name. So now you're used to some sort of protection for computer intellectual property.
Yeah.
Well, in 1962, you couldn't patent software, you couldn't copyright software.
It just went everywhere.
Well, it was open source by definition.
Yeah.
Anyway, being in the users group and the users all knowing about it, most of the PDP-1s had the minimal configuration, which was the display and 4K of memory. And so, not having a better demonstration program, people used it to show things off and to show off their new computer.
Show off how cool the PDP-1 is.
And so, since about half of the PDP-1s went into research laboratories or universities, there were a lot of people who saw Spacewar demonstrated. And some people actually got copies of the code and translated it to the computer they had, and other people just looked at it and said, "Oh," and wrote their own.
They just reverse engineered it by looking at it. So let's see. So when indie game developers create games with potentially contentious subject matter, like Spacewar, which is about kind of the Cold War, the war in space. They often take flack for doing so. So in creating Spacewar during that time, did you take any flack at all?
No, well, there was no flack for the subject matter. There was flack to some extent for the idea of using computers to play a game.
You're wasting time. It's valuable computer time. Let me see.
It should be noted that I wasn't the first one to write a game for a computer.
Yeah, Higginbotham did with the Tennis for Two.
Yes,
right?
But that was an analog computer.
Ah, okay. Also, one interesting thing, you notice that the display is circular on the display, which is interestingly not square, and the resolution of the display is 1024 by 1024, which is a rectangular dimension. So why did it come out circular?
This has to do with the history of digital. The engineers who started digital equipment had worked on Whirlwind, which was an MIT project, which was turned out to be the prototype for the SAGE air defense system. And so one of the things they had was a simple CRT display on Whirlwind. And I was fortunate, Whirlwind was still running when I first showed up at MIT. And the people in the computer center had worked on Whirlwind, and they arranged a tour just before it got shut down. And one of the things they had was a program called the Bouncing Ball, which had displayed a wall and a floor with a gap in it. And they pushed the ball, which was a spot, off the
wall,
top of the wall, and had it bounce realistically down, and either off the screen or down through the hole. And apparently this was viewed as a very magic program in Whirlwind, because at one point it was crucial in getting further support for the project.
Needed some physics, something like that.
Yeah, well, it convinced the physicists that, yes, you could simulate things on a digital computer. And I had seen that, so the idea of doing things on a display was not new to me. The tube itself was used in World War II radar. With the mechanical scan radar, there's a problem in telling what's going on. And so if you have a spot on the screen that shows a target and it moves, the slow trail that it leaves shows you which direction it's going and that it's moving. Oh. And this is very interesting because that's the airplane you want to know about.
Yeah.
So they had done it on Whirlwind. When digital was started, the engineers had by and large worked on Whirlwind. They thought a display was a good thing, and so the obvious thing was to design a display like Whirlwind.
Okay.
And in many ways, the PDP-1 is a transistorized version of Whirlwind.
Oh, okay. Interesting. So when you finished, I guess, it kind of finished like the first version of Spacewar, and it was running on the PDP-1, the game basically got copied somewhere else, right? It left the university, it went to another university. I know it...
Well, it was in the users group, so you could just order it.
Okay, so you just...
If you had a PDP-1, you just order it from the users group, you get it.
You get it, and then you take it somewhere else, and basically the game spread among all the universities that could actually create, basically enter the program and run it.
Yeah. Well, I was talking to, I volunteer at the Computer History Museum in Mountain View, where we have a restored PDP-1, and I say essentially this, and other people give their version of it. I was talking to a guy who had worked on he was a physicist, and he had worked on another computer. It wasn't a PDP-1, but it did have a display, and its intent was analyzing bubble chamber pictures. But he had taken the versions, there were 3 or 4 different versions of Spacewar floating around in his installation, and they were all buggy.
Wow. And they were not ones that just the parameters were changed, but people actually tried to add more code to it. Right?
Yeah, and, well, it was a different computer. So
it was totally...
Yeah. Anyway, he had brought them all together and debugged them so that you had a stable game.
Nice. And when the code got moved around to different universities and people were starting to do stuff to the game, they had to translate it from one assembly language, the PDP assembly, to another assembly if it was on a different system. Interestingly, this was kind of the time of the first mod community, I think we would call it. Only within the university, but people were trying to make the game cooler,
there was this mod community
faster.
that started up trying to get me to change the parameters.
Right. And you put them in there, and then everyone stopped doing
Yeah,
it.
I suppressed that one.
But even at the very beginning, while you were making the game, the expensive planetarium was kind of a mod to the game.
Yes.
It was like somebody else put code in there.
Oh, yeah. Well, it was, one of the lessons is that games are always collaborative. It's clearer to me with written word and movies. But the thing is, if you're creating stuff, you need a critic. You need an editor.
Yeah. Critique.
And you better pay attention to what the editors have to say.
Yeah, and so everyone was playing it, and they're giving they're giving feedback, but they're also coding.
Well, later on, much later on, I was working briefly in the computer game business, and at the time, the rule of thumb was that for each hour of engineering time in writing the game, you needed to spend about an hour of testing time in order to get the game to be adequately reliable.
Yeah,
well, I did a back of the envelope calculation on Spacewar. I got somewhere between 100 and 1,000 times more testing time than it took me to write it.
Well, actually, it probably didn't take you so long to write it. It took you more time to just get the thing in the computer.
Yeah. Well, and this leads me to my boast, which is no outstanding crash reports, no user complaints, support still available.
Every month, twice a month at the Computer History Museum. It's a record. It should be Guinness World Record there.
Well, one of the secrets is it's damn small.
Yeah, it was like 2,000 lines of assembly.
Around 2,000 lines of assembly code.
Cool.
Including the outline compiler and the expensive planetarium.
Everything else in it. Okay. So the legend is that when Spacewar reached Stanford, finally went around all over the place.
Well, Stanford had a PDP-1.
Yeah, so it had to, they had the machine that they didn't have to translate to. They could
Yeah.
just get it over there. Students who played it just went nuts. This was basically, it blew their mind because it was the birth of a new medium, computer games. They got to see this for the first time when they got to see your game, and they said it was better than psychedelic drugs back then. Did you know that people's minds were being blown by computers?
Well,
Spacewar.
I think Spacewar was the first computer game where people actually wanted to come back and play it again.
It was a game, and it was
Yes,
fun, and it was
the other
balanced so
games-
you felt like it was your fault if you lost.
Yeah, well, you did have to learn something.
Yeah, you had to learn the gravity.
Yes.
Basically about gravity, prediction, acceleration, all that. Let's see. I'm not sure if I've mentioned this before, but the PDP-1, the processor on that was pretty slow. Back in the late 70s when home computers started, back with the Apple I and the Apple II and then the Commodore and all that, they were based on the 6502, which was a 1 megahertz computer, but the PDP-1 was a 0.1 megahertz computer. And to get the game to be able to refresh it at 50 hertz.
No. 12 to 15 hertz.
Oh, that was, that's really fast.
Well, there wasn't, it was timed entirely by memory cycle. Fortunately, PDP-1s always came at one speed, so I didn't have to worry about upgrades.
But everybody that was putting stuff into the main loop had to worry about ruining the display, basically.
Well, yeah, because one of the big challenges was reducing the sine and cosine computations, because doing sines and cosines and square roots was very leisurely.
Yeah. Do you know if there was the idea of pre-generating cosine and sine lookup tables?
There
Like that?
wasn't enough
No memory?
space to make that attractive. Actually, my numerical analysis wasn't terribly good, and I wasn't up on all of the possible programming tricks. So it might be that if someone wanted to re-engineer it, that they could do that.
Okay.
But it was...
It was tough. You had to use the instruction, and you had to wait for it, basically. The PDP-1, when you were entering code into it, used a thing called a flexowriter,
Yes.
which was a very expensive typewriter.
No, it was, well, it wasn't expensive typewriter allowed you to do what a $5,000 flexowriter did on a $120,000 computer.
Okay.
It was a little faster and a little better, but it was still, for doing program editing, by and large, you used the flexowriter. The flexowriter, some of you have met the Model 33 and paper tape.
I don't know if anyone here has seen paper tape. Paper tape is, it's
There's somebody up there.
somebody's seen paper tape. The flexowriter punched into basically paper
Anyway,
tape.
it was a modified IBM electric typewriter, which roared along at 10 characters a second. And it had a paper tape reader and paper tape punch on it and some controls. So when you were typing in your source code initially, you would type it on this flexowriter and punch paper tape. And then when you got the code done, you'd run the paper tape through the flexowriter again, printing out and getting a neat copy, and you go off and proofread that. Yes, paper tape, 8-channel paper tape.
Yeah, because I've seen paper tape with just one stripe.
There's also was 2-channel paper tape for Morse code, and there was 5-channel paper tape for teleprinters and teletype communication, and there was 6-channel paper tape for typesetting.
Wow. All the things we didn't know. Yeah, that's pretty cool.
Well, you want to see a really cool machine, you should see a linotype machine running off paper tape.
What channel? What, 8-channel paper tape?
6-channel.
6, okay.
The linotype, is there anyone who knows what a linotype is? Oh, I better
There's some
tell you.
people, yeah.
A linotype machine is an 1890s mechanical machine which manipulates the molds for individual letters. So you have a keyboard, and you type at it, and you assemble these molds, and then it automatically casts the line in type metal. And one of its charming features is if you don't fill out the line, the typecasting operation doesn't go right.
Uh-huh.
And the error message is it squirts hot type metal at your foot.
Nice. So give it a bunch of blank stuff.
People, typographers remember to fill the line.
Yeah. So they took a linotype machine and they just kind of retrofit it with.
In the 60s, that was a popular thing.
Nice. Did they fix that error?
No.
Bug in the machine?
No, it's innate.
Oh, it just happens. You can't stop it. So when you were writing Spacewar, I think everybody might understand at this point. You were writing the game in assembly language,
Yes.
which is, in a modern language like say C, which some of you here might know C. More of you might know a higher level language than that, like Java or Python. To print something on the screen is as easy as just saying print, quote, and then your text. But on a PDP or doing something in assembly, it's a lot of instructions to do that.
Not bad. That was another great feature of the PDP-1. It had a simple typewriter interface.
Did it have a font in it?
Well, no, the font was built into the mechanics of the typewriter.
Oh, okay.
It was roughly Courier 10.
Yeah.
So there were two instructions: type out and type in. Nice. And you put the character you wanted in the I/O register, and gave the type out instruction, and the typewriter started up and typed the character. If you wanted to, you could check that it did it because you could do a type in afterward and see what the typewriter claimed to have printed.
So you debug that way.
Yeah. But there was that was very straightforward. Most of the other typewriter interfaces were line at a time or would only take numbers or something like that. So that was a relatively revolutionary feature of the PDP-1,
Nice.
that it was simple. So input-output wasn't too bad.
Yeah.
What was really bad was the typewriter, because the typewriter was an IBM electric typewriter, which was designed to be used by people. And it turns out people don't type at 10 characters a second for 2 shifts.
Yeah. Usually it's a lot faster than that.
And furthermore, it was a modified version. IBM had one version that was too expensive for digital, which was had a solenoid for each key and just pulled on the key, and a contact for each type bar, and told you which type bar hit. So they had a modification from an outfit called Soroban Engineering, which had a mechanical 6-bit to pull on the key converter, and a mechanical what key actually hit the platen to 6-bit converter. And they weren't too well designed, it turned out.
Oh, no.
So it was infamously unreliable. When I was working on Spacewar, very quickly MIT got 2 typewriters. So there's one to keep on the computer and one for the maintenance guy to fix. And
just keep swapping them out.
yes, during the week. But
Nice.
Several times in debugging Spacewar, which I did tend to do on the weekends, because I had a day job. Several times I couldn't get anything done one weekend because both typewriters had failed by 6 o'clock Friday evening.
Jeez. Because everyone's banging on them all week.
And and they'd been swapping them out all week, but
Jeez.
2 of them had failed after the maintenance guy went home Friday.
This is probably like analogous to people writing code with, or making games with like faulty tools that crash and just do crazy stuff. And you have to keep on running and trying to get your work back and all that. It's hardware this time instead of software. So when the game basically went around, and you heard about Spacewar being played at other universities around the country?
Oh yeah, and it turns out 2 of the arcade game builders, at least, had seen Spacewar somewhere.
Like Cinematronics, right?
And the guy who wrote the first Asteroids had played Spacewar at Stanford.
Oh yeah, that's right.
And so, it was like me seeing the bouncing ball.
Yeah.
Okay, we know how to do it. We know you can do it. The only problem is, can you do it on what's available? And
the computer,
$120,000 computer isn't suitable for an arcade.
It's funny that was 18 years later, though, when Asteroids came out.
Yeah.
And I think the Cinematronics one came out before that. Does they even have a date on that one?
Well, there was a Cinematronics one. There was Galaxy, which was Bill Pitt's one, which was famous for being in the Stanford Student Center.
Right, and that's what's at the Computer History Museum right now.
That's running. Bill Pitts has restored it.
Nice.
And, so it's available all the time at Computer History.
Yeah, I think this was Tim Skelly wrote this one for Cinematronics, and this is the one that people saw in the arcade, I guess.
Well, and it also showed up as a home computer.
Yeah,
and there was a home game system that was based on the Cinematronics stuff. Somewhat later.
Yeah, the Vectrex.
Yes.
Yeah. Has anyone heard about the Vectrex? Yeah, many of you? All right, cool. So yeah, Vector. It's funny, so Spacewar didn't have a vector display. The nice thing about a vector display is you can just say point, start a point, draw to this point, and it physically moves.
But their explosions aren't as good as mine.
Yeah. he had to plot every point, right?
My explosions are really something like explosions.
It's like particle effects, basically, because all he had was dots.
The Cinematronics explosions are just the vectors fly off in different directions.
Yep. Yeah, that was easy for them, just streak in different directions, but you had to actually put every dot on there to make it cool, like the original particle effect generator. So how did you feel about people playing the game, hearing that they liked it, and then modifying the game around the country, and then finally seeing it popularized in arcades where everybody could play them?
Well, I learned a lesson. One of the things that the arcade games did, which I would have resisted because it was unrealistic, was they added viscosity to space. So the starting levels... Oh,
the friction?
The starting levels, when you got the spaceship going too fast, so it was just going zoom, 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 zoom across the screen, if you just took your hands off the display, then things would calm down so you could see what was going on. And that was...
That's not realistic.
Yes.
Just suppress hyperspace.
But it made it much easier to learn.
Yeah. Okay, so in closing, I'd like to congratulate and thank you for the incredible accomplishment of kickstarting the world of computer game development, a tidal wave of inspiration that continues to rise to ever higher levels over 50 years after your initial supernova.
How
Thanks
purple.
a lot.